All right, welcome to the electronics class for October the 28th. So I've looked over the homework assignment that you guys turned in for the diodes, and pretty much everybody got 100%. That last question there, you could see that, I basically gave you the answer in the problem statement. And so almost all of you figured that out, but one of you didn't. But so how are you guys feeling on diodes? You have a good understanding of how they work?
Yeah, pretty much.
Yeah.
Okay, pretty straightforward. Now, I trust that before you turned in the assignment, you clicked on the link that I gave you and you read about the diodes. And so I trust that when you did that, you learned that there's actually more to just diodes, more to diodes than just what we talked about. There's different kinds of diodes. There's Zener diodes and there's Schottky diodes and all sorts of things. It's not my intention to go into the distinctions between these different types of diodes. This is an introductory electronics class. And so if you're going to worry about the distinction between a Zener diode and a Schottky diode, that's the subject for a more advanced electronics class. As far as anything that we're going to do in this class, we can just treat them all, a diode's a diode. All right, so now that we understand diodes, we are now ready to move on to the next step, which is transistors. And like I said last time, transistors are super important to basically all electronics that you guys use are based on transistors. So you definitely need to understand transistors and how they work. But there is one thing, before you understand how a transistor works, we should take a minute and talk about how a diode works. And when I say how it works, I don't mean just how do you hook it up, like that's what we talked about last time, but I mean, if we were to look inside the diode and find out what is it that makes a diode so that it flows electricity one way and not the other way, what's happening inside the diode? We need to do that because that's the basis for how a certain type of transistors work. Now, there are more than one type of transistors. We're going to talk today just about the earliest kind that they first developed, something called a bipolar junction transistor. Those are nice and simple. And then later they developed a different type of transistor, but we'll talk about other one later. Okay, so before we can understand the one, we have to understand the other. So, okay, so I'm going to share this with you. All right, if you were to look inside of a diode, what you would have is you'd have two pieces of a special semiconductor material called silicon. And you may recall from the very beginning of the class, way back a couple months ago, we talked about the fact that there are conductors, there are insulators, and then there's a thing called a semiconductor. And in fact, tell you what, just so there's no confusion here, let me kind of repeat what we did because I realize it's been a couple months. So if you were to look at the spectrum, over here you have something that's a perfect conductor. And over here you have something that's a perfect insulator. Okay, and basically nothing is perfect. I mean, even if you were to take a piece of metal, which is considered to be a great conductor, metal isn't a perfect conductor. It has some resistance. If you take a copper wire, up until now, we've always treated copper wire as if it had zero resistance. It doesn't have zero resistance. It has negligible resistance compared to the other things that we're working with. If we put a resistor or a transistor or a thermistor or something in there, those things have much more resistance than the wire does. So we can neglect the resistance of the wire, but it doesn't have zero resistance. So even metals, they're over here, they're close to being perfect conductors, but they're not perfect conductors. And something like rubber or wood, That's over here. Those things are, well, actually wood. Wood's a special case because wood depends on the moisture content of the wood. But let's say rubber or glass. Okay. So rubber or glass, those are over here. Those are really good insulators, but they're not perfect insulators. Okay. So when most people think of the word semiconductor, they think, well, okay, it's some material that's somewhere in between, right? So they think a semiconductor is something that's not really a great conductor, not really a great insulator, is somewhere in between. Like for instance, wood, is, especially if the wood is still fresh, so it's still got lots of moisture in it. It's not really a conductor, not really an insulator, it's in between. So this is what most people think. So when you're taking your notes, which, because I know you always take notes for what we do, right? So I want you to write this little thing, and then I want you to put a great big X through it, because that turns out that's not what the word semiconductor is defined to mean. Now, they could have defined it that way, and it would have made really good sense if they had defined it that way, but that's not the way they defined it. So if you have something in the middle here, we should call it a partial conductor, not a semiconductor, because the word semiconductor has already been taken and it means something different. A semiconductor is something where if it's pure, and when I say pure, what I mean, it has no contaminants. Okay. So like, for instance, if you have a bunch of silicon, if you have a crystal of silicon and every single molecule in that crystal is silicon, there's no other molecules snuck in there while you were making it. Okay. If it's absolutely pure, then it turns out it's a good insulator. Maybe not perfect, but a darn good insulator. Okay. But if it's impure, which means it does have contaminants, and it can be really, really small. I mean, it could be like maybe 1 part per million. Okay. Even something, contaminants. Okay. Even something as seemingly small as 1 part per million, that's enough that it can make it be a good conductor. Okay, so this is what a semiconductor is. Okay, all right, so silicon is the most commonly used semiconductor out there, but there are others. There's things like gallium arsenide and a bunch of them. Okay, so what we have inside of a diode is on the left side here, you see what they call P-type silicon. And what that means is it's silicon that has some contaminant purposely added in. And so if you were to look at it, the contaminants that are purposely added in have an extra positive charge. So in other words, an electron has been stolen away. Okay, so if you look at the silicon here, it's it's mostly silicon. I mean, when we talk about contaminants, we're talking part per million level here. So it's mostly silicon, but every once in a while you get an extra little atom here that has a missing electron. So it's a positive. So the left side of this diode is a good conductor because it's got contaminants in it. And over here on the right side, it's also contaminated, but in this case, it's contaminated with a bunch of material that has an extra electron. And so we call it N-type silicon. So if you take the left side all by itself, that would be a good conductor. If you take the right side all by itself, that would be a good conductor. But if you put the two of them together side by side, really interesting things happen. Okay, so what happens is this. Let me I have to turn off annotation in order to change slides, and then I got to turn the annotation back on again. Really annoying. Okay, So this right here is what we call the junction. Okay, so that's where the p-type silicon and the n-type silicon are touching each other. Okay, so when they're touching each other, what happens is that some of the extra electrons from the n-type, they migrate over here and they combine with the positive charge, and so you'll see these move over here. And so what happens is in this region right here, the extra plus charges here get canceled out by the minus charges, and so this region here, it now is basically pure silicon, because all of those extra plus charges and extra minus charges canceled each other out. So we have a little region right at the junction. It's a thin region, but it's thick enough to do the job. So it is essentially pure silicon. Even though there were contaminants, the contaminants canceled each other out. Okay, so now because we have this thin layer of pure silicon, well, pure silicon is a good insulator, right? So that means that electricity cannot flow, right? So what we have here is a diode that's just sitting there. Now, it hasn't been hooked up to electricity yet. It's just sitting there, and it's got this naturally occurring depletion layer, or sometimes it's called the depletion region. Okay, so now what happens if we connect this up to a battery? So let's say that I've got, let's see, let me go back here. So here is a battery. Here's the plus side of the battery. Here's the minus side of the battery. So if we connect the plus side up to this side of the diode, connect the negative up to this side of the diode, then what happens is we have a whole bunch of plus charges, and they come in, the battery pushes these plus charges in there, and so that pushes the plus charges over here. So this region here with all the plus charges, it gets squished over this way. And the minus charges here, you can think of the battery as pushing minus charges out this side. And so the concentration of minus charges increases here. So that pushes the minus charges over here. And so what happens is it squeezes this depletion layer down until the two regions touch each other again. So we've squashed the depletion layer. And so then once that happens, then we no longer have this pure silicon in here. And so now electricity can flow. So it flows through there just fine. What if we hook up the battery the other way around? Okay, so here's our battery. Let's put it upside down. So here's the minus side up here. Here's the plus side. So we hook up the plus side over here to the cathode, right? So what's happening is the minus side of the battery is trying to suck out the positive charges, and the plus side of the battery is like sucking out the negative charges there. And what happens is our depletion region gets bigger, not smaller, because the plus charges are all sucked out. Okay, so if we hook up a diode backwards, what happens is we've increased the depletion region, increase the thickness of the depletion region. And as long as we have a depletion region there, that's basically pure silicon. And so nothing's going to flow. So you see, this is how a diode works. And so it's all based on what we call a p-n junction. So this is p-type silicon because it has more positive charges than normal silicon would. This is n-type silicon because it has more negative electrons than normal silicon would. And so each one by itself would be a good conductor, but if you put them together, you get this depletion region in here. And so it now becomes a diode. So that is how diodes work. And that's also the basis of how transistors work. But before I do that, give me thumbs up or thumbs down. Does that make sense? So yes means, yeah, it makes sense. No means you need a little more time on this. So type it into the chat box here. Not seeing anything in the chat box. So you guys, okay, good. Had me worried there for a little while. All right, so this is making sense. Okay, good. All right, so now we understand how it is that diodes work. Okay, well, that means we are now ready to learn how it is that transistors work, or at least the type of transistor that we're going to be talking about today. Okay, so we're going to talk today about a type of transistor that's called a bipolar junction transistor. And when we say bipolar junction, what it means is that the transistor inside of it, it has this same, PN type of structure, and it has this junction here, but it's just modified a little bit. So let's go take a look at it. Okay, so how about if we do this? We're going to take what's essentially two diodes, and we're going to hook them up back to back. So if this, whoops, sorry, wrong way. Okay, I have to turn on annotation before I do that. Okay, so if this was all we had, if this wasn't here, do you see what we have here is we have a PN junction. So remember this, we're pretending that this isn't here. All right, so if we take a battery and we hook it up the plus side and the minus side, if we hook up the plus side to this and the minus side to that, we've got a diode. And so electricity will flow through the diode just fine. Okay. And if we look at it the other way, okay, what if this part of the thing wasn't here? What if all we had was this? Well, again, we have a diode because it's that PN junction. Okay, so if we take the battery here, let me put the battery up here. So if we take the battery here, if we hook the plus side up to the P side and hook the minus side up to that, again, the electricity will flow through. It'll flow through like this. It'll flow through just fine. So what we got is basically two junctions that are back to back. So the P type is common to both of them. Okay, so now something really interesting happens when we do this. Okay, let's suppose that we take our battery and okay, so here's our battery, and here's the plus and here's the minus. So let's try hooking the plus side of the battery up to here. Let's hook up the minus side of the battery to here. Is current going to flow through here? What do you guys think? Is current going to flow through here and back into the negative side of the battery? So let's take a vote. Type in the chat box, yes if you think the current's going to flow through there, no if you think it's not. All right, I'm seeing lots of no's. All right, so Isaiah, you are one of the people that voted no. Why is current not going to flow, Isaiah?
I'm in the car right now, so it might be a little bit noisy.
Okay.
But it wouldn't hook up because it's essentially a battery is positive and negative. The positive charges flow to the negative side. But for this, it's negative to negative, so nothing's going to go anywhere.
Interesting thought. How about Eric? What's your thought on why did you say no?
So I thought like there would be what's those things in between the P type and N type called again? I forgot.
The junction?
Yeah, I think there would be like those in between each of them so they wouldn't go through.
Okay, all right. I see where you're coming from. Here's a good way to think of it, guys. So remember this part right here is basically like a diode that's pointed this way. This part down here is basically like a diode that's pointed this way. All right, so if I take my battery, here's my plus minus. Okay, if I hook up the battery like this, okay, so it is trying to push the current through here like this. So when the current comes to this diode right here, is that diode going to let the current through? Answer, no, because this diode only lets current flow this way. If we try to flow through it this way, the diode's going to say, nah, not going to allow that to happen. Okay, so if we hook up our battery, the way that we've got it shown here, so that the plus side of the battery is connected up to this side. This diode right here is going to say, nope, I'm not going to let you flow through here. So then we say, okay, let's try hooking up our battery the other way. Okay, so let's turn the battery around so that we put the plus side of the battery down here and the minus side of the battery up here. All right, so now the battery is trying to flow the current through this way. And so this is what the battery is trying to do, but is it going to make it? No, because this time the lower diode is going to sit there and say, no, 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 because it will not allow electricity to flow this way through it. It only allows electricity to flow through this way. So you see what we got here. When we have back-to-back diodes like that, no matter which way we try to get the current to flow, one of the diodes is going to say, nope, I'm not going to allow that. Let me just fix something really quickly here. Okay. All right, so no matter which way we try to get the current to flow, one of the diodes is going to say, no, it's not going to allow it to go. But something really interesting happens if we connect up something to this middle terminal right here. Okay, so let me clear my drawing. Okay, so if I take my battery, if I connect it up to the middle part here, so current can flow, right? Because this is the PN junction, and if you have a diode, then current can flow from the P part into the N part. So remember that you always go from positive to negative. So if I hook up my battery like this, it will allow current to flow. And what's really interesting is, let's say I have two batteries. I've got a little battery over on the left side, and I got a great big battery over on the right side. Okay. And so first off, let's say that I haven't got this battery hooked up yet. Okay. And so I've got my big battery here, and I've got it hooked up here because I'm trying to flow electricity through here. That's what I want to do. Okay. But I'm not able to do it because this part of the transistor is a diode, and it's saying, no, I will not allow that. So even though we're trying to flow current through here, the transistor is saying, nope, I'm not going to allow that. But as soon as we hook this guy up so that current flows through this guy, all of a sudden what happens is that fills the P region here. That it changes the P, this what we call the base. It changes the structure of this. If it has electricity flowing through it like this, it then opens it up and it allows that electricity from the bigger battery to flow through. Okay, so electricity can flow through a transistor, but only if we have turned the transistor on. And the way that we turn the transistor on is by sending a little bit of current through here. And what's really interesting is the current that flows through here can be really small. And when I say really small, I mean like it could be even less than 1 milliamp. I mean, it might be a couple microamps, just a tiny little bit of current through here. That's all it takes to turn on the transistor. And once we've turned on the transistor, then all of a sudden we can get a very large current flowing through the transistor. But then as soon as we stop sending current this way, then all of a sudden that turns off the transistor, and then also all of a sudden the big current stops flowing. Okay. Now, if you want to know more about why that works, my response would be, well, wait until you take a little bit more advanced physics. Because I don't want to spend too much time going into the nitty-gritty details, because you'd need to understand more physics than you currently know. But basically, if you think about it in terms that I just described, okay, that little tiny bit of current that you put into what's called the base, that turns on the transistor, and so then you can get a lot of current that flows through from the top end to the bottom end of the transistor. Okay, so now that you know that, Okay, so you see what we've got here is this. And so here in this symbol you see over on the right here, you can see it's being represented as if it's two diodes back to back. And so remember, the way that diodes work is that the arrow shows which way it flows, and it always flows from the P side to the N side. And here they both have a common P side, and it flows to the N side. So if you were to look at the transistor, you see we have N type, P type, and then N type. So we call this type of transistor an NPN transistor. Now we could have done it the other way around if we wanted to. Instead of hooking up the transistor, instead of hooking up the diodes so they had a common a P side, we could have hooked it up the other way. Okay, we could have hooked it up like what you see here, so that instead of the current flowing like this, we have it going the other way around, so the diodes are both pointing inwards. So then what we have is on the outermost region we have P type, the innermost region we have N type, and then the outer type we have P type again. So a PNP and an NPN transistor both could work, and in fact both do work as transistors. But if we try to mix NPN and PNP, students tend to get confused. So what I'm going to do in this class is I'm going to focus all our attention on an NPN transistor. I just want you to be aware that there are other types of transistors out there. They're called PNPs, and they work similar to, but not exactly the same as what an NPN works as. Okay, and later maybe we'll talk about PNPs later, but for everything we're going to do today, we're going to focus on the NPN type transistor, because that is the one that most people like to use the most. Okay, all right, so now what you're seeing is the schematic symbol. So if you were to look on a electrical schematic, a piece of paper where they show the batteries and the resistors and everything, but instead of actually drawing a picture of a battery and a picture of a resistor, they include that special little shorthand symbol. So what you see right here, this is the shorthand symbol for an NPN transistor. And you'll notice that it has 3 connections to it. One connection is called the base. And that is the thing where if you want to turn on the transistor, that's where you want to send the current in. And then it's got this one side right here that's called the emitter. And so when you connect the base to the emitter, so if you put the emitter at some negative, or if you put the emitter at 0 volts, so you put this basically at ground. Okay, and then you put this at some positive voltage. Okay, so then current can flow from the base to the emitter. So that's what turns on the transistor, is when you have current flowing from the base to the emitter, that turns it on. So then that allows for a really big current to flow from the collector to the emitter. So the C here, that stands for collector, and the E stands for emitter. Okay, and then the B stands for base. All right, so when you look at a transistor, you're going to see it's got 3 leads, got a base, base, collector, and an emitter. And so this would be a good time to actually look at a real resistor. So let me, let's see, hang on a sec while I get, I'm going to open up Word here. Why is it not letting me do this? Hang on. Okay. Okay, so Word is not what I meant to say. Okay, here we go. Okay, so I've opened up my browser. Let's go to Tinkercad. Let's go to circuits. And guys, I recommend you do the same thing, okay? I'd like you to open up Tinkercad also and go to circuits and create a new circuit. All right. Now, over here on the right where we have all the components we can play with, if I scroll down here, I don't see any transistors. I do see this thing right here that it comes in a package that looks very much like a transistor, but it's not a transistor. So you got to be careful. Just because something looks like this, that doesn't mean it's a transistor. In this case, it's actually a temperature sensor. So that's different. So we don't have transistors in our collection of components here, at least not in the basic collection. So if we click on here and we go down, instead of basic, we want to go with all. So let's click on that. Now we have a whole bunch of more stuff that we didn't have before. You have to scroll down quite a long ways, but if you scroll down far enough, here we are. Okay, so you'll see under the section that's called power control, here we have an NPN transistor, and BJT means bipolar junction transistor. So it's the kind of transistor we talked about. Over on the right side, you'll see we have a PNP transistor. So it's that other type of transistor that where the diodes are hooked up. You still have two diodes, but they're hooked up nose to nose rather than tail to tail. And then we also have a couple other types of transistors down here. And this is called an NMOS transistor, and this is called a PMOS transistor. These guys, MOS transistors, they work differently. And you are going to learn about them, but not today. I don't want to flood you with too much stuff all at once. It'll confuse you. So today we're going to focus on an NPN bipolar junction transistor. Later, we're going to learn about these other types of transistors. All right, so let's click on the NPN transistor and let's drag it in here. Okay, so there it is. And you guys, I recommend you do the same thing. So let's zoom in on it. You notice how it's got three leads here. One of them is labeled collector, the other is labeled base, the other is labeled emitter. All right, so if we take this guy and we turn him on his side, then he's lined up kind of the way that we were, in fact, he's lined up exactly the way that we were doing it before. So you can think of this as a diode, and actually two diodes back to back. So you can think of this as we got one diode going this way and the other diode going this way. Oops, I didn't mean, let me fix that last thing. I need to put the triangle there before I put that. Okay, so this is the same as that. So if that's the case, we should be able to find out what is the threshold voltage for each one of these diodes. Okay, so this is the first thing that I want you guys to do, is I want you to ignore this guy, focus all of your attention on this guy, and say, hey, from here to here, it's a diode just like the ones that we played with before. I wonder what the threshold voltage, or it's also called the forward voltage, I wonder what the forward voltage of that diode would be. So in your homework last night, you remember we had two different types of diodes. We had the LED and we had the regular diode. And the threshold voltages were very different for them. So first thing I want you guys to do, and I want you to do it right now while we're all together, is let's measure the threshold voltage of the lower diodes. Okay, so when I say lower, I mean, so we're going to look at these two leads and we're going to treat them as if they were one diode, and we're going to find out what is the threshold voltage of the lower. And then I'm going to do the same thing, but this time I'm going to focus our attention on the upper diode right here, and I'm going to find out what is the threshold voltage of the upper diode. So what we're going to do is we're going to connect this side to the plus side of our power supply and this side to the minus side. Okay. And let's see what the threshold voltages are for each of those two diodes. Is it going to be the same? Is it going to be different? Let's find out. So you guys know how to do that? Remember how we did it before? We need a power supply, right? So I'm going to go back to the power supply. Where'd my power supply go? Oh, it's not in the basics there. Okay, so let's go down. So we have to go into all to get power supplies. All right, so there we go. So here's a power supply. Okay, so do you guys remember how to measure the threshold voltage? I'm going to sit here. I don't want to do it for you. Okay, so Henry has now measured both of them. Henry, can you tell me what numbers you got?
The threshold voltage for both of them is 0.6 volts.
Okay, very good. And I see that Eric is getting the same thing. Are the rest of you guys also getting the same thing? Okay, good. All right, so it looks like the threshold voltage is 0.6. Okay, so let me just verify that. Okay, so remember you got to hook it up the right way. If you hook it up backwards, it's not going to work. Okay, so there I've got them hooked up. So I'm going to start off at, okay, so I'm going to start my simulation. I want to start off at 0. Okay, so if I go to 0.2 volts, nothing happens, or at least I don't get any current. So I go to 0.4, still don't get anything, go to 0.6. Okay, I'm starting to get something. Okay, so I agree with you. It looks like my threshold voltage, at least for the lower diode, is 0.6. Now, what about the upper diode? Okay, so I bring it up here like that. Okay, so let's do the same thing. Let's start the simulation. So if I go to 0.4, I get nothing. I go to 0.6. So yeah, okay, I'm starting to get something. All right, so the threshold voltage is the same for both the lower one and the upper one, okay? And it is 0.6 volts. Okay, so good. So we've started to characterize our transistor here, and we see that it does in fact behave exactly as if it was two back-to-back diodes. Okay, so now let's see what could we do with a transistor that might be useful. All right, well, I have a circuit already made here. Let me go back into my my circuit collection. And so you see here, I've got one circuit here that says transistor as amplifier. I'll come back to that one later. I want to start off with this one where it says transistor as switch. So let's tinker that one. Okay, so let's get rid of this guy here. Okay. All right, so what you're seeing here is we've got an Arduino, and it's hooked up through a transistor up to this thing that you see up here, and that is intended to represent this, okay? So this is one of the motors that we use in our robotics club, and this is a very strong, very powerful motor, and it requires a lot of voltage in order to work. If we were to just take this motor and hook it up to the Arduino, so because you guys know now how to turn on lights using Arduinos, and you know how to turn on buzzers using Arduinos. And so you would think, well, I could also turn on a motor using an Arduino, right? So if I just take the negative side of the motor and I plug it into ground, and if I take the positive side of the motor and I plug it into one of the Arduino pins, okay, then you would think that if I tell the Arduino to turn on that pin, you would think that that would turn on the motor and it would run the motor. Well, bad news for you. It's not going to do that for two reasons. One is that when you turn on an Arduino, the voltage that you get on the pin is about 5 volts. Actually, it's slightly less. It's actually about 4.5, 4.6 volts. When people talk about it, they talk about it as if it's 5 volts, but it's actually slightly less. Okay, so I'm going to call it 5 volts, even though not. Okay, so the best possible voltage you can get when you turn on one of these Arduino pins is 5 volts. 5 volts is not enough for this motor. This motor requires 12 volts. Okay, so that's not going to cut it. And also, this motor requires a lot of current. When you hook up this motor, the current can be, I mean, it's not going to be measured in milliamps. It's going to be measured in amps. This thing can pull 2, 3, 4, 5, 6. In fact, this thing could even pull like 30 or 40 amps under certain circumstances. And there's no way in the world that this poor little Arduino can put out even 1 amp, let alone 10 amps. And in fact, this is one thing that we should talk about. Now's as good a time as any. If we're working with real Arduinos, you have to be careful because you can easily destroy an Arduino. If you hook up an Arduino to something that pulls a lot of current out of it, you can destroy the Arduino. You have to be careful. The maximum amount of current that you can put out of an Arduino pin, any one pin, is about 20 milliamps. If you try to exceed that, you're going to have some problems. Okay, so 20 milliamps is the most we can put out, and 5 volts is the most voltage we can get. So that clearly is not going to work to run this poor motor, unless we hook it up using a transistor. Okay, so let's see how the transistor could solve our problem for us here. Okay, so let me zoom in on this. All right, so remember how it is that transistors work. Remember what I said was that if you put a small amount of current here, so let's say we turn on pin 13. So let's say we've got 5 volts here, and 5 volts is enough to send current in here through the from the base to the emitter and out here. So now, and I'm even going to put a resistor here. So we're just going to have a tiny trickle of current. It might not even be 1 milliamp. I mean, it could be a milliamp, but it could just be a tiny trickle of current is all we need going through here. Once we do that, that then turns the transistor to the on condition, and that allows a very large current to flow through here. All right, so now let me zoom back out again. I have to turn off annotation before it'll let me zoom out. Okay, so what I have here is I have a power supply right here, and I've got this power supply set for 12 volts. So 12 volts is what this motor needs. So this motor here needs 12 volts. So the power supply is going to give it what it needs. The Arduino is not. All the Arduino is going to do is it's just going to put out just a little trickle of current, which is enough to turn on the transistor. And so when we turn on the transistor, that allows the current to flow through it. All right, so you see what's going to happen? Now, if we look at the code, you'll see I've got a really simple code right here. I've just got it set so when I activate it, it's going to set pin 13 to high for 2 seconds. Then it's going to set pin 13 to low for 1 second, and it's just going to cycle through that again and again and again. All right, so let's see what happens. I start the simulation, and so you see the motor turning, and then the motor stops, and then the motor turns again. Okay, so you can see maybe it's hard to see here. Maybe if I zoom in, oh, you can see that, right? Okay, but so you can see the motor spins for a little while, and then it stops, and then it spins for a while, and then it stops. Okay, and the thing that's causing it to spin and stop is the fact that the Arduino here is turning on the transistor for 2 seconds, and then it turns the transistor off. Okay, so the motor is getting its power from the power supply, not from the Arduino. The Arduino is just acting as a switch. So does that make sense to everybody? Okay. All right. So what I'd like you guys to do right now is take 5 minutes, and I want you to basically duplicate what I've done here and set up a situation where the Arduino is used to turn a motor on and off. And I'll just sit here and wait. I'll go ahead and pause the recording. There's no sense in running the recording. So I want you guys to basically duplicate what I've got here. All right, so I've just restarted the recording, and I see that pretty much everybody now has it. So congratulations, you have now just used the transistor as a switch. It's basically an on-off switch where you can take a tiny bit of weak low voltage electricity, and using that weak low voltage electricity, you can turn on and off a switch in order to control really high voltage, high current electricity. So that's a very, very important application of transistors, but it's not the only application. Okay, so another application is, let's see, okay, here. All right, let's suppose that we've got some signal that it's a very weak signal. I don't know, maybe we have a radio telescope and we're searching the universe for extraterrestrial life. Okay, so we've got our radio antenna. We've got one of those satellite dishes, and we've got it pointed into outer space, and we're trying to receive signals either from aliens, or maybe there's a spaceship that's out there orbiting Jupiter, and we want to communicate with that thing. But the radio signal we're getting from it is really, really weak. Well, what we can do in order to increase the strength of that signal is we can take our transistor and we can use this really weak signal that you see on the left side here. This is the weak signal. And we can feed it in into the base of our transistor. And so what happens then is that when the signal comes through here, that allows a much stronger current to flow through here. And so when the signal goes high, that allows a lot of current to flow through here. And when a lot of current flows through here, then that means that the voltage is going to drop because a whole lot of current is flowing. So when our weak signal goes high, our output signal goes low, but it goes low by a lot more than this does. Our weak signal here might only be 1 millivolt, whereas our output signal here might be 100 millivolts, or it might even be 1,000 millivolts, or it might even be more. Okay, so this is called the gain. So now you'll notice that the output signal is inverted. When the weak signal goes high, the output signal goes low. That's okay. We can deal with that. The important thing is the output signal is a lot stronger than the input signal. So we're using the transistor as an amplifier. Okay, so what we want to do is we want to know what is the gain of this amplifier. Okay, so let's suppose that our weak signal here has a maximum strength of 1 millivolt. And let's suppose that we look at the output signal here, and let's suppose that that's 10 millivolts. So in that case, the gain would equal 10, okay? Or if it was 100 millivolts, then the gain would equal 100, okay? And, you know, maybe it's 1,000, the gain could be 1,000. So transistors have pretty high gain. And in fact, when you're talking about a transistor, we have a special word for it, because gain is a word that's used for for other purposes as well. So when we're talking about a transistor, instead of calling it a gain, we're going to call it beta. So we're going to say, what is beta for a certain transistor? And as you saw in the Tinkercad collection, you saw there are different types of transistors, and they're probably going to have different gains, different betas. So you know what I'm going to have you do next is I'm going to have you measure the gain of the NPN transistor. And that's going to be your main homework assignment for tonight. So let's see, how would we go about measuring the gain of a transistor? So I'm going to go back into here again. So this shows using the transistor as a switch. So let's go back into here. Okay, so here I've got transistor as an amplifier. So let's tinker that. And so this is what I want you guys to build as your homework assignment for tonight. Okay, so what I've done is I've got two power supplies, and I've hooked up this transistor so that the power supply on the left is the one that's going to power my input to the transistor. And I want my input signal to be really weak. So I'm going to use a resistor here, and you can see that the resistor that I've used is a 1 kilo ohm resistor. So I want you guys to do the same thing. So take a power supply over on the left side, hook it up so that the output of that transistor goes into the base of my, the output of the power supply goes into the base of the transistor, but it has to go through a 1 kilo ohm resistor in order to get there. So that 1 kilo ohm resistor is going to guarantee that we have a really weak current. Okay, so when we turn that on, then if we look down at the bottom part of our, in fact, tell you what I want to do here. I don't want to give this away. So I want to hide something here. What can I hide it with? Battery. Let me bring in a battery. Not because I want to use it as a battery, but because I want to hide something so that you can't see it. Okay, so so you won't be able to see how much current is flowing through there. Okay, so now I'm going to start my simulation. All right, now notice my power supply on the left. I can change my voltage there, and that will change how much current is flowing. So if I put it down to 0 volts, obviously 0 amps is going to flow. So let's take it up to 0.2 volts. Okay, still getting nothing. Why are we getting nothing? Because we have not exceeded the threshold voltage of the diode that's inside the capacitor. So 0.2 volts is not enough to turn, or I called it a capacitor, I meant a transistor. So 0.2 volts is not enough current, or not enough voltage to turn on the diode that's inside my transistor. And if I go to 0.4, okay, still not there. If I go to 0.6, okay, still doesn't look like it's working here. So how about let's go to 0.8. Okay, now I'm getting something flowing. Okay, now if I were to look at, if I were to move this battery so you could see what's hidden behind the battery, you would see that some current is now flowing from the power supply on the right. You would see that the amount of current that's flowing through this guy is going to be much, much bigger. Okay, so this here, I'm going to call this I input. Okay, so this is going to be our input current. This guy right here, I'm going to call this our output current. The word output might not be the best word to use, but it's the current that flows as a result of our input current. So I'm going to use the word output, even though I would prefer to have a different word, but I can't really think of a better word right now. Okay, so if my input current was 10 milliamps and my output current was 100 milliamps, then what would my beta be? What would my gain be? Somebody type that in the chat box. Okay. If I do this test and I find that for an input current of 10, I get an output of 10 milliamps, I get an output current of 100 milliamps, what would my gain be? So if I do 10 times the gain equals 100, so where X is the gain, what is X in this case? All right, I see somebody said 90, but it's, yeah, this is not an addition thing. This is a multiplying thing. Okay, so 10. All right, so in this case, if these were the numbers that I got, my gain would be 10. Okay, but what if I don't get those numbers? What if it works out, let's say that I have 10 milliamps as my input, but let's say that I have 175 milliamps as my output. Then what would my gain be? Okay, so remember, I input multiplied by the gain, which by the way, I'm gonna use the correct word for it. The gain here is actually called beta. And this symbol that I just used that looks like a B, except it's got a longer tail at the end of it, that's the Greek letter beta. So my input current multiplied by my beta equals my output current. Okay, so Eric and Henry both have it. They both sent me private messages. So if these are the numbers that I use for my input and this is what I get for my output, my beta would be 17.5. Okay. All right. So your assignment, should you choose to accept it, and even if you don't, is to build a circuit that looks identical to what you're seeing right here. And now I'm going to cover it up because I don't want to give it away. I want you guys, you have to do the work here. So we're going to start the simulation and you're going to see what the input current is and see what the output current is and see what the beta is. And then I want you to turn up the voltage here so you're going to have a higher input. See if the beta changes, okay? And then turn it up to a higher voltage yet. And so now we've got a much higher input current. We're going to have a much higher output current. So play with this and see what happens. See if the beta when you're at low input currents is the same as the beta when you're at high input currents. And tell me what number that beta is. Now, I don't want you to tell it to me right now. I want you to type it into Canvas, okay? But I do need to warn you one thing. If you go too high on your input, did you see what just happened on my power supply? Let me turn on this. So I want you to look at the voltage on my power supply. If I keep my down here at low voltages, you see that my output, my power supply on the right, the voltage on that thing never changes. Now the current does. The current is going to change big time, but the voltage never changes unless if I go up here too high, boom. Okay. What I've done is I've reached the point where I have now saturated my transistor. And so I've reached what's called saturation mode. And when you read the homework assignment tonight, because you guys know, if you look on Canvas, you'll see I've given you a link. And the link tells you about transistors. And I want you guys to read that thing before you do the homework. And what you'll find is that if we push our transistor too far, we've reached saturation and then weird things happen. Okay, so do you guys understand what your homework assignment is? So type into the chat box, yes or no. Yes means I understand what the homework assignment is. No means I don't. All right. Well, in that case, I'm going to leave you guys to do it. Now, I'd like you to leave the Zoom on so that if you run into problems, I'm here to help you. So I'm going to turn off the recording. but I'm going to stay on Zoom, and let's all stay together on Zoom. And if you have any problems, then speak up.